Solids have very strong IMF strength. So before we can go anywhere, we have to discuss what I mean by IMF. Okay, so IMF stands for intermolecular forces. And intermolecular forces are exactly what they sound like. They're the force that is connecting the molecules. They're the force between the molecules. So if you have molecules of some sort of gas or liquid or solid, there is a force of attraction between those molecules. And remember, we talked about water as being polar, and water has very strong intermolecular forces because it's polar. All right, so solids have very strong IMF strength, and that's going to come up over and over and over again. Solids also have a short internuclear distance, which means the distance between these is very small. Solids are not fluid. Now, the word fluid to you might mean beverages, but in science, the word fluid means that it can flow. So we'll see how liquids and gases are both fluids. Solids have high density, and that comes from its short internuclear distance. Solids are not compressible. So if I have a solid object, like the cap on this water bottle, it means that I can bend it, but I can't compress it. It is rigid. So these are properties of solids. Now I could go on and talk about solids, all different types of solids. There's amorphous solids and crystalline solids, but unfortunately we're running out of time in chemistry, so we're gonna have to save those for another day. Now I want to talk to you about liquids. Liquids have stronger intermolecular forces than gas, but less than solids. Liquids are like the middle child, right? Liquids are fluids, which means they can flow. Liquids have high density and they're not compressible. So they're very much like solids right here. If you were to think about a container that contained a solid and a liquid, right? You would have the solid particles here and maybe the liquid particles here. Either way, they're not filling the container and they're not able to be compressed. Liquids diffuse slower than gases, but faster than solids. You might be thinking, how do solids diffuse? I hear about diffusion when I think about cellular biology, and I think about gases diffusing. Well, they can because of the kinetic molecular theory. Liquids evaporate. So this water right here, if I were to leave this water out with the cap off, eventually it may evaporate out of the container. All right, now if I were to put the cap back on the liquid, I could stop the evaporation from happening. And that's because equilibrium will be established, right? Initially, it will evaporate out. If we have a cap on, it'll evaporate out after some time. Some molecules will start to come back, and at equilibrium, there will be equal amount exiting as there is entering. Evaporation refers, if you don't remember, from a liquid turning to a gas. It's kind of basic what you would have learned in second and third grade there. So equilibrium is where there's a balance between the evaporation rate and the condensation rate. Vapor pressure is another characteristic of gases that's a little bit trickier to understand, okay? Vapor pressure is expressed in terms of atmospheres. So I want to remind you about what we talked about the other day with pressure. All right, I live here on planet Earth, and I have the atmospheric pressure on top of me. This means I have all sorts of gas particles, oxygen, nitrogen, carbon dioxide gas, all of that atmosphere is sitting on top of me. That's called the atmospheric pressure. And the atmospheric pressure is standard at 1 atm. Vapor pressure, as far as liquid goes, is the opposite of that. Okay, so if I have a liquid, this liquid has a certain pressure pushing out on it to want to become a gas. That's how I think about vapor pressure. And vapor pressure can be affected by temperature, by changes in temperature, as well as molecular bond strength, which is just another way of saying intermolecular forces, or IMFs. A liquid's vapor pressure indicates the extent at which it evaporates, right? If we have very strong intermolecular forces, if this purple liquid here has very strong forces between the liquid, it's not going to want to turn into a gas. It's going to want to stay a liquid. High intermolecular forces mean that the vapor pressure is less.
After you've kind of seen the results of what happens when you start studying intermolecular forces, and we start making a little bit more of a condensed phase, such as solids and liquids, you start getting all these unique properties of solids and liquids. Liquids have quite a few unique ones: viscosity, surface tension, and one of the more unique ones is vapor pressure. That's a very special case, and that's probably another thing completely. So let's just think about it. If you take water in a container and you allow it to start evaporating, the space above the surface of the water will start getting water molecules. That means it's a gas now, and gases impart pressures. So as that builds up, what's going to happen is these particles floating above the water can go back into the water unless they're whisked away. So if you put a lid on the container, all the particles are trapped, so the water starts going back into the water phase, or I should say the water vapor goes back in. As this happens, you finally reach a state at which the exiting evaporation rate equals the entering condensation rate, and you reach what we call equilibrium. So when those two rates equal, you establish a constant pressure inside your container. And that pressure is called the vapor pressure of that liquid. In the case of water, you would say it's the vapor pressure of water. It's an example of what we call dynamic equilibrium, meaning when you look at the thing, you can't tell anything's happening, but in actuality, there are billions and billions of molecules leaving the surface of the water, and there's also billions and billions re-entering, and they are exactly the same rate, so there's no net change, but you have established what we call a vapor pressure.
So like I said, his video does a nice job of showing the liquid leaving, or the particles leaving the liquid and then coming back in. So if we were to heat these liquids, if I were to heat the liquids in these containers, it would cause the particles to move faster. That's what the kinetic molecular theory says. The higher the temperature, the higher a liquid's vapor pressure, right? The more likely that liquid is going to want to evaporate. And this is what brings me to boiling point. Boiling point is the temperature at which the vapor pressure of a liquid equals the external pressure. You probably have learned about boiling point. Let's think about water. You probably have learned about the boiling point of water as being simply this: 100 degrees Celsius. That's the temperature at which water will boil. But it turns out it's a little bit more complicated than that, because water boils at 100 degrees Celsius only if it's at STP, or standard pressure, really is what we're looking for, or 1 ATM, or 760 millimeters of mercury. So boiling point depends on the atmospheric pressure and the intermolecular forces. So when we talk about 100 degrees Celsius, that's the normal boiling point of water. If I were to go up onto a mountain, all right, if you look at the back of the rice-a-roni container, there is high altitude cooking directions. So you can imagine me at the top of the mountain cooking my rice-a-roni, all right? I have that same atmosphere as I had before, except there's less of it on top of me. I'm at the top of the mountain, so there's less atmosphere sitting on top of me. The atmospheric pressure has decreased. So now My liquid that I'm going to try to boil at the top of the mountain doesn't have as much force pushing down on it. And therefore, it's going to boil at a lower temperature, right? As the pressure increases, as I come down the mountain, the boiling point is going to go up. So if I'm cooking that rice-a-roni at the top of a mountain, it's instead of boiling at 100 degrees Celsius, maybe the water is going to boil at 95 degrees Celsius. So the high altitude cooking instructions tell you to cook the rice-a-roni longer because it's boiling at a lower temperature. Now, if we think about intermolecular forces, this is polar molecules. More polar molecules are going to have a higher boiling point. That's to say that water, which is very polar, has a higher boiling point than, say, I don't know, acetone, which is less polar. So that's solids and liquids, right? I would say solids and liquids are in a class of their own. If you think about solids and liquids, they have very similar properties. They're not compressible. The particles can move in a liquid, but not as much. And then we've got a gas, and all rules change with the gas because now the particles are zooming all over the place and they're fluid and they're really nothing like the solid or the liquid. So gases can expand to fill any container. And in chemistry class, that means that we're going to have to do a lot of math problems with that. Gases are fluids, which means they can flow. They have very low densities. That has to do with all that empty space that's between them when they're filling the container. They can be compressed. So if I imagine in this water bottle, there's gases up here at the top when it's sealed. Make sure it's sealed. And you press it, I can compress the gases at the top. Lastly, gases undergo what we call diffusion and effusion. Diffusion is if I were to empty or open a perfume bottle in the side of the room, the scent from the perfume would reach the entire room. That's diffusion. Liquids also undergo diffusion. And they also do something called effusion. This is probably a new word for you. It means that gases are escaping tiny holes, like maybe in the side of a balloon or something like that. So let's watch this video about gases.
Every minute of every day, you breathe without even thinking about it. Your body does it on its own from the day you're born until the day you die. You have muscles contract to bring oxygen, a gas, into your lungs, which is then transferred by your bloodstream to every cell in your body. Gases are strange. We can't see them, but we know they're there because we can feel them. What we experience as wind is really trillions and trillions of gas molecules slamming into your body. It feels good, right? Science is based on observation. Unfortunately, we cannot observe gases with our eyes, they're too small. We have to use our other senses to make observations and draw conclusions. Observations are then compiled and we create a model. No, not that kind of model. A model is a way scientists describe the properties of physical phenomena. First, gases always move in a straight line. We don't really have anything to demonstrate this with because gravity always pulls objects down. So, imagine a bullet fired from a gun, and that bullet goes on at a constant speed in a perfectly straight line. That would be like a gas molecule. Second, gases are so small, they occupy no volume on their own. As a group they do, blow up any balloon and you can see how that volume changes. But single gases have no volume compared to other forms of matter. Rather than calculating such a small amount of matter, we just call it zero for simplicity. Third, if gas molecules collide, and they do, remember these are assumptions, their energy remains constant. An easy way to demonstrate this is by dropping a soccer ball with a tennis ball balanced on top. Because the soccer ball is bigger, it has more potential energy, and the energy from the larger ball is transferred to the smaller tennis ball and it flies away when that energy is transferred. The total energy stays the same. Gases work the same way. If they collide, Smaller particles will speed up, larger particles will slow down. The total energy is constant. Fourth, gases do not attract one another, and they don't like to touch. But remember rule 3, in reality they do collide. Finally, gases have energy that is proportional to the temperature. The higher the temperature, the higher the energy the gases have. The crazy thing is that at the same temperature, all gases have the same energy. It doesn't depend on the type of gas, just the temperature that gas is at. Keep in mind, this is a model for the way gas particles behave, and based on our observations, gases always move in straight lines. They're so small that they're not measurable on their own, and they don't interact with one another. But if they do bump into one another, that energy is transferred from one particle to another, and the total amount never changes. Temperature has a major effect, and in fact, all gases at the same temperature have the same average energy. Whew, I need to go catch my breath.
Okay, so what he was discussing there were assumptions about gases. And in order to make those assumptions, we have to define what we call an ideal gas. So, an ideal gas is a hypothetical gas that perfectly fits all of those assumptions that he was talking about, all of the assumptions of the kinetic molecular theory. All right. Gases are a lot of empty space. These are just what he talked about, just in different words. They're really far apart compared to their size. A liquid's volume expands about 1,000 times. So if you were to drink liquid nitrogen, it would blow up because it would expand. I mean, before it froze you, it would expand about 1,000 times in your body. Gases are easily compressed because of all this empty space. The second thing he mentioned was gas particle collisions are elastic. I keep showing you this picture because it's very simple, but it's a really good representation of the kinetic molecular theory. These particles are bouncing around and bouncing off of each other. The word elastic means no loss of energy. So as these gas particles hit each other, they bounce right off each other like a billiard ball. Energy can be transferred to each other, but it's not lost. Gas particles are in continuous random motion, and gas particles are not attracted to each other. And lastly, like he was mentioning, the temperature depends on the average kinetic energy of the particles. Now, we know that these aren't 100% true, all right? Like, especially one like this. Gas particles are not attracted to each other. Well, according to dispersion forces, there is a little bit of attraction. So real gas particles that actually really exist do have their own volume, albeit very, 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 very tiny. And they do attract each other. Again, those dispersion forces. Even if you have an O2 molecule that's totally nonpolar, it's going to have a certain amount of attraction. Gas behavior is most ideal and fits those assumptions at low pressures and at high temperatures. I think it's much like your most ideal when you're in a low pressure scenario sitting on a beach in a high temperature. Also, non-polar atoms and molecules is going to lead to more ideal gas behavior. Turns out most of the gases we talk about here in Chem 1, O2, N2, CO2, are non-polar. All right, so yesterday we looked at a graph that contained solids, liquids, and gases, and it was, there was a lot of connections between them. I made a connection for you that said that solids can turn into liquids, and liquids can turn into gases, and solids can also turn into gases, and I called that sublimation. So I was showing you that everything could happen in a lot of different directions. It turns out I showed you the more complicated graph first. This graph takes pressure into account. This graph that I'm going to show you right now is at a constant pressure, okay? So it's at a constant pressure, and if I were to define that, it would be standard pressure or 1 atm. All right, so In this graph right here, this side is temperature and this down at the bottom is technically time. But over here on the bottom as well, we could call this heat. We could call this energy. There's a couple different things that you could put at the bottom of this graph. So don't think that the bottom of the graph is set in stone, because a lot of times it's either time or heat or energy. As we continue to look at this graph, you can look here at this portion of the graph. This is where the substance is a solid. Right here, this portion of the graph is where the substance is a liquid. And way up at the top here, this is where the substance is a gas. So you can see as you add heat or energy or time goes by, it turns from a solid into a liquid into a gas. Another thing I want to point out is that you can have a very cold solid or a warmer solid. You can have a colder liquid or a warmer liquid, colder gas or a warmer gas. Now let's talk about those flat portions of the graph. We have a flat portion right here and a flat portion right here. The thing that you should notice right away is one is bigger than the other. This area right here is boiling. All right. This is where the liquid turns to the gas. And in the opposite direction, this is condensing. This portion right here, it's really kind of small. In that direction is melting. And back in the other direction, this is right here, back in this direction, we call that freezing. So remember how I told you that liquids and solids are really similar to each other? So it turns out that to go from a solid to a liquid doesn't take nearly as much energy as to go from a liquid to a gas. So it takes a lot more energy to enter that gas phase. Another thing that I want you to notice is that the temperature does not change during a phase change. So the temperature stays the same. All of the energy goes into the phase change. All the energy goes into melting it. All of this energy goes into boiling it. And so when you look at heating curves, solid, melting, liquid, boiling, gas, the temperature change section, or the portion of the graph that does this, is where there's a change in molecular motion. All right. The phase change, or where the temperature remains constant, is where there's a change in molecular arrangement. So that's when we're going from a solid to a liquid or a liquid to a gas. All right. Let's look at these ones just a little bit more specifically. We go to another chapter called thermodynamics, where these will be, we'll go into more detail about these. But the melting point is equal to the freezing point. So if you were to say water freezes at 0, you could also say that water melts at 0. The higher the intermolecular forces, the higher the melting point. This should make sense. If the molecules want to stick together, that's going to give them high intermolecular forces, and they're not going to want to change phase into that liquid or to that gas. So I can ask you questions like this. Which of these has a higher melting point? Polar things or non-polar things? Well, polar things are stickier. Remember the sticky molecules. So they're going to not want to break apart. So they have a higher melting point. What has a higher melting point? Covalent molecular substances or ionic? Definitely the ionic. Take, for example, sugar, which is covalently bonded, versus salt. Sugar is going to melt in your kitchen. We call it caramel. Salt is not. So sugar has a much lower melting point than salt. Vaporization. So I have mentioned boiling and I've also mentioned evaporation. Both of these are when a liquid turns to a gas. So both boiling and evaporation both count as vaporization. They're very similar, but obviously they're different. They're different terms. Boiling is when we see bubbles throughout the liquid. So I have a picture here just in case you've never seen things bubble. Um, there are liquid particles within the liquid that are trying to vaporize. Evaporation just happens at the surface. This is this idea that I leave the cap off and the surface molecules are going to evaporate. The molecules at the surface gain enough energy to overcome the intermolecular forces. Vapor pressure can be less than the atmospheric pressure. Remember, boiling is where the atmospheric pressure equals the vapor pressure. The word volatility in chemistry, people think it means something like really exciting, but when a liquid is volatile, all it means is that it evaporates more quickly. So you can have volatile liquids, and all it means is that you leave it on a table and it's going to evaporate more quickly. Again, also determines on temperature and intermolecular forces. So both boiling and evaporation apply to a liquid changing to a gas. Evaporation is at the surface and boiling is throughout the liquid. Here's a picture that I found online. There's a lot of this stuff online because there's a lot of students that really confuse boiling versus evaporation. The last one I want to leave you with is where we kind of ended the other day, and that's sublimation. Now my heating curve, my basic heating curve doesn't really, right, doesn't discuss sublimation. I don't talk about going from a solid to a gas because in order to talk about sublimation, I have to think about pressure. All right. And that's because sublimation, like boiling, is when the vapor pressure equals the external pressure. Except this time, it's not the vapor pressure of a liquid, it's the vapor pressure of a solid. Not something we talk about very often, but that's certainly what's happening there. The vapor pressure of, say, dry ice is equaling the external pressure. Sublimation happens in dry ice. It also happens in those solid air fresheners that just seem to kind of disappear. Those are actually subliming.